You know, um, Usually when we talk about getting the absolute best, most cutting edge performance out of a piece of tech, there's this like underlying assumption that you just have to pay the toll.
Right. Yeah, there is a literal cost to genius.
Exactly. I mean, if you want top tier graphics, you buy the massive power hungry graphics card, right? Or if you want the fastest car, you pay for the premium fuel.
It's basically been the accepted law of physics and computing for decades.
Yeah, it's this totally binary choice, brains or budget. You either get the genius level performance and it costs you an absolute fortune in computing power,
But
or,
you go for the budget option and you just sort of accept that the system is going to make mistakes.
right, but then you step into the world of state-of-the-art generative AI and suddenly that trade-off is just being completely hacked.
It really is. It's a huge paradigm shift.
So today's deep dive is exploring this brand new, fascinating research paper. It's titled RelayLLM, Efficient Reasoning via Collaborative Decoding.
Great paper. Highly, highly recommend reading it.
And for you listening, I mean, whether you're a developer trying to run capable AI locally on your own devices, or you just, want to understand how the future of this tech is going to scale without literally melting our global power grids.
Which is a real concern, by the way.
Oh, absolutely.
Yeah.
But yeah, we are looking at a secret to making AI insanely efficient today. So, okay, let's unpack this, because to understand why RelayLM is such a massive breakthrough, we first kind of have to understand the glaring inefficiency in how AI works right now.
Yeah, we have to look at what we can basically call the all-or-nothing trap.
The all or nothing trap. I like that. What does that look like in practice?
Well, in the current landscape of artificial intelligence, we basically have two distinct categories of models. First, you have your large language models, right? The LLMs.
Right, the big ones from the major tech companies.
Exactly. These are the massive 8 billion, 70 billion, or even trillion parameter behemoths. And they sit in these remote data centers.
Humming away, using ridiculous amounts of electricity.
Yeah, and to be fair, they are brilliant. I mean, they can execute highly complex mathematical reasoning, but they are incredibly slow, and the compute required to run them is just staggering.
Like they need those massive server farms with thousands of specialized chips just to answer a simple prompt.
Right. And then on the exact opposite end of the spectrum, we have small language models, or SLMs.
And these are getting a lot more popular recently, right?
Oh, definitely. These might be 1 billion or 2 billion parameters.
Yeah.
And they're fantastic because they are blindingly fast. Like, you can run them locally on a laptop or even a smartphone.
And they're practically free to operate compared to the big guys.
Exactly. But, and here's the catch, they hit a cognitive wall very quickly
Right.
because of how autoregressive models work, predicting one word at a time. If a small model makes a single, tiny logical error early on in, say, a multi-step math problem,
It just snowballs from there.
yeah, that error compounds
Yeah.
and the whole output just completely falls apart.
So if I'm a tech company and I'm building an AI application, I have a really serious structural problem here
You do.
because I want to give my users the brilliant, flawless answers of the massive LLM, obviously, but I definitely do not want to pay that massive computing cost for every single little query they type into the search bar.
No one wants to pay that. So the industry standard solution right now is a workaround called cascading, or sometimes you'll hear it called query level routing.
Query level routing. Okay, how does that work?
You essentially put a router, which is just a piece of software acting like a traffic cop, right in front of your models.
Okay.
When a prompt comes in, the router takes a quick glance at the text and estimates its difficulty.
Like it's grading the question before answering it?
Sort of, yeah. If it looks like a simple factual question like, what's the capital of France, it routes the query to the fast, cheap, small model.
Makes sense.
Yeah.
Save the money.
But if it detects a complex logic puzzle or a multi-step math problem, the router flags it as hard and sends the entire task over to the massive, expensive LLM to handle from start to finish.
See, that feels incredibly wasteful to me.
Oh, it is.
Like, that's like hiring an expensive Michelin star chef to cook a whole meal from scratch just because you don't know how to chop one tricky onion.
That is actually a perfect analogy.
Right, because, I mean, even on a hard math problem, doesn't the small model actually know how to do like 90% of the work?
Yes, exactly.
It knows how to read the problem, it knows how to set up the basic equations, do the simple arithmetic, so why are we throwing the baby out with the bathwater and making the massive model do the easy parts too?
You just hit on the exact premise the researchers behind RelayLM started with. Query-level routing is just a massive source of computational waste.
Because it's an all-or-nothing handoff.
Right. A small model is entirely capable of handling the vast majority of reasoning steps in a given prompt. It usually only gets tripped up at one or two critical, complex bottlenecks in a logic chain.
The tricky onion.
The tricky onion. But because the router offloads the entire query to the large model the moment it smells difficulty, we are burning immense amounts of compute, having a genius-level AI do basic arithmetic.
Yeah.
Stuff the small model could have done locally for free.
Okay, so clearly the researchers needed a way to intervene only when the small model actually gets stuck. Like not before the problem starts, but right in the middle of generating the answer.
And that brings us to the core innovation of RelayLLM. It's called token-level collaborative decoding.
Token-level collaborative decoding. So breaking it down word by word, basically.
Essentially, yeah. Instead of relying on a traffic cop router looking at the whole query up front, RelayLM turns the small language model itself into the active controller.
Oh, wow. So the small model is put in the driver's seat of its own generation process.
Exactly.
But wait, how does that actually work mechanically? I mean, these models are essentially just highly advanced autocomplete engines, right? They just predict the next token.
Right.
How does an autocomplete engine pause and ask for help?
Well, it's a really clever use of the model's existing architecture. The researchers trained the small model to generate a very specific command sequence when it calculates high uncertainty.
High uncertainty, meaning it knows it's about to mess up.
Yeah, it's essentially injecting a special control token into its own output stream. It's actually very similar to the tags models already use to separate a system prompt from a user prompt.
Okay, so what does this tag look like?
The sequence literally looks like an HTML tag. It's an open bracket, the word call, a variable number n, and a closing bracket.
Oh, so it's literally a dedicated text string acting as a trigger, like call in.
Yes. And the surrounding system is programmed to monitor the output for that specific control token.
Got it.
When the small model generates that call tag, the system intercepts it and pauses the small model's generation right there.
It literally freezes it.
Yep. Then it takes the entire context window, so the original question,
Yeah.
plus whatever reasoning the small model has already typed out, and hands that baton to the massive LLM.
Okay, and what was that in variable you mentioned, the number?
Crucially, that n in the tag represents a variable number of tokens. The small model is telling the large model to generate only the next n number of tokens.
Wait, really? So it can say, I only need 10 words of help?
Exactly. Maybe it just needs 10 tokens of expert guidance to get past a logic bottleneck.
Just chop the tricky onion and step aside.
Yes, the large model generates those 10 tokens, and then the system takes the context, complete with the expert's addition, and hands the baton right back to the small model.
And then the small model just picks up where it left off.
It reads what the expert just did, incorporates that logic, and resumes solving the rest of the problem entirely on its own.
It is a literal relay race occurring in the GPU memory space. That is so cool.
It's incredibly elegant.
Well, here's where it gets really interesting, because looking at the source material, they highlight this classic math riddle to illustrate the exact mechanism we're talking about. It's the 100 cats and 100 rats problem.
Oh, yeah. That is a perfect stress test for the cognitive limits of small models.
So the riddle goes like this, for everyone listening. If 3 cats can catch 3 rats in 3 minutes, how long does it take 100 cats to catch 100 rats?
Which sounds simple, but it's a trap.
Totally. A human glancing at that, and certainly a small AI model, usually jumps to the intuitive but completely wrong answer, which is 100 minutes.
Right, because they just follow the numerical pattern, 3, 3, 3. So obviously 100, 100, 100.
Yeah, they recognize the surface level pattern rather than pausing to calculate the underlying rate of action.
Exactly.
But in the paper's case study, we see the RelayLLM system tackle this exact prompt. The small model starts reasoning perfectly fine. It writes out the premise of the problem.
Setting the stage.
Right. But right when it reaches the point where it has to deduce the actual rate of catching per cat, it realizes it's in tricky territory. So instead of guessing and failing, it outputs a call tag. It specifically outputs call 8.
It is specifically asking the massive LLM for just 8 tokens of help.
8 tokens. So it passes the context window over, and the massive LLM steps in.
Yep.
And the large model outputs exactly this. Each catches 1 rat in 3 minutes. That's it. That's the 8 tokens.
It just clarified the foundational logic of the rate.
And then, boom, the baton goes back.
Yeah.
The small model reads that 1 cat catches 1 rat in 3 minutes and perfectly finishes the math on its own. It correctly concludes that 100 cats working simultaneously will also take exactly 3 minutes to catch 100 rats.
What's fascinating here is that dynamic prediction. The small model dynamically chose to ask for exactly 8 tokens.
It didn't just ask for an open-ended answer.
No, it evaluated its own confusion and decided, I just need a tiny nudge. The researchers actually tested this against alternatives.
Oh, like what?
Well, they tried hard-coding a system where the small model was forced to always ask the large model for a fixed block of help. Say, exactly 100 tokens every single time it got stuck.
Like giving it a strict, inflexible allowance.
Exactly. But dynamic prediction, letting the small model decide how much help it needs, proved vastly superior.
Really? How so?
The dynamic relay LLM achieved the exact same high accuracy as the fixed 100-token model, but it consumed significantly less compute.
Because it wasn't wasting tokens.
Right. It proved that sometimes a model needs 50 tokens to map out a complex algebraic equation, but sometimes it literally just needs 8 tokens to clarify a rate.
Wow.
Forcing a fixed token allowance just recreates the computational waste we were trying to avoid with query-level routing in the first place.
Okay, I am completely tracking with the mechanics of the relay, and the token economy is absolutely brilliant. But I have to push back on the fundamental premise here for a second.
Sure, go ahead.
It's one thing to say the small model evaluated its own confusion. We are talking about a 1.7 billion parameter neural network here. It doesn't have a soul, and it certainly doesn't have human self-awareness.
Definitely not.
So how on earth do you train a relatively simple AI to accurately recognize its own ignorance and actively choose to ask for help?
That is the crux of the entire paper, honestly. Teaching metacognition. The ability to think about your own thinking or knowing what you don't know to a machine.
It sounds impossible.
It's difficult, but the researchers solved this using a highly structured two-stage training framework.
Okay, let's explore how they actually pulled that off. What's stage 1?
The first stage is what they call a supervised warm-up. If you just take a raw, small model and try to use reinforcement learning to teach it when to ask for help, it will fail instantly.
Why?
Because it doesn't even know the literal syntax of the call command token. It's never seen that specific string of characters in its vast pre-training data of internet text.
Oh, right, because it's a made-up tag for this experiment.
Exactly. So the warm-up phase is essentially giving it the vocabulary to raise its hand.
Okay, but there's a risk there, right? If you train a small model on the outputs of a large model to show it how to use the tag, doesn't it start like mimicking the large model's writing style?
Yeah, and then it loses its own underlying statistical distribution.
Right.
That is a very real problem. It's called distribution shift. And the researchers handled it beautifully.
How'd they dodge it?
They didn't use the large model's text for this stage at all.
Really? What did they use?
They took the small model's own previously generated correct answers to math problems, and they programmatically inserted the call tags into that text at random intervals.
Oh, that's smart.
Yeah. They fine-tuned the small model on this modified data. So it learned the physical syntactical act of outputting executable control tokens without fundamentally changing its own voice or probability distributions.
That makes total sense. So the model learns the mechanics of how to physically deploy the tag. But, I mean, that still doesn't teach it when it's appropriate to use it, right? It just knows how to type it.
Right, and that is where stage 2 comes in. Policy refinement with reinforcement learning.
Okay.
Specifically, they utilized an algorithm called GRPO, which stands for Group Relative Policy Optimization.
GRPO. Okay, break down the group relative part of that for us. How does that differ from just standard reinforcement learning?
Well, in standard reinforcement learning, a model tries an action, gets a score, and adjusts.
Trial and error.
Basically. But in GRPO, instead of just trying one single path to solve a math problem, the small model generates a whole group of different attempts simultaneously.
Oh, wow.
Yeah, so some of those attempts might use the call tag early, some might use it late, and some might not use it at all.
So it's parallel processing its own potential strategies?
Yes. Then the system grades all those attempts and calculates an average score for the group. And here is the relative part. Each individual attempt is then judged relative to that group average.
Okay, I think I see where this is going.
If one specific pathway, say one where it asks for 10 tokens of help at step 2, solves the problem faster and more accurately than the group average, the mathematical weights for that specific behavior get reinforced.
Well, here is the operational problem with just rewarding the right answer. If I am building this and I just give the AI a reward every single time it gets the math problem correct at the end, The small model is going to realize very quickly that the large model is a genius.
It is a genius, relatively speaking.
Right. So it's just going to get lazy and spam the call tag on every single word to guarantee it gets the reward. Like, why wouldn't it?
You've just described the exact failure mode of a naive reward system.
Right.
The small model would become totally dependent on the teacher, which completely defeats the purpose of efficiency. To prevent this, the researchers designed a highly specific, difficulty-aware reward system.
Difficulty aware.
Yes. It acts as a carrot and stick across 3 different scenarios to shape the model's behavior perfectly.
Okay, let's deduce how this works. If the goal is efficiency, scenario 1 has to be when the math problem is relatively easy, right? Something the small model can handle.
Correct.
In that case, you'd want to heavily reward it for not bothering the big model at all, like a bonus for independence.
You would, and they did. They call it the student solvable scenario. If the small model solves the problem correctly without ever calling the large model, it gets a massive boosted reward of 1.5x.
Oh, wow. So it mathematically incentivizes the model to trust its own capabilities on easier tasks.
Exactly. Don't call the boss unless you really have to.
Right. But then scenario 2 would be the hard problems, the ones where the small model genuinely lacks the parameters to solve it alone.
Yes. They call this teacher dependent. And here's where the stick comes in.
Oh, boy.
If the small model faces a complex problem and gets the final answer wrong, specifically because it refused to ask for help.
Because it stubbornly tried to guess its way through.
Exactly. It gets a strict penalty of -1.
-1. So it actively punishes overconfidence.
Absolutely. It teaches the neural network that guessing blindly when you are out of your depth is mathematically worse than asking for help.
That is brilliant. It creates a really powerful boundary of self-awareness, and I assume scenario 3 covers the extremes?
It does. It's called teacher unsolvable. This is when the query is so insanely difficult that even when the small model asks the large model for help, the final combined answer is still wrong.
Oh. Well, in that case, I'd assume nobody gets a reward since the answer ultimately failed.
You'd think so, but surprisingly, the system still issues a small exploration reward to the small model, as long as it at least tried to use the call tag.
Wait, really? Even though they got it wrong?
Yeah, even though the outcome was a failure, the training framework reinforces the process of recognizing an impossible situation and reaching out to the expert.
That is a remarkably nuanced way to shape a behavior.
It really is.
Because of those 3 scenarios, the small model is optimizing for a very specific policy. Solve independently when you possess the knowledge, seek help the precise moment your internal probability drops, and never, ever guess blindly.
Exactly. So we know the theory, and the training mechanism is incredibly elegant. But the ultimate test is whether this actually bridged the capability gap between small and large models in practice.
Let's look at the numbers. The researchers ran their empirical tests using the Qwen3 model family.
Right.
They designated a 1.7 billion parameter model as the student SLM and an 8 billion parameter model as the teacher LLM.
And just to ground those numbers for the listeners, a 1.7 billion parameter model is small enough to run smoothly on the processor of a standard smartphone.
Oh, nice.
Yeah, very lightweight. An 8 billion parameter model, on the other hand, requires significantly more RAM and processing power. You are looking at needing a dedicated high-end server GPU to run it at speed.
Okay, so a massive difference in hardware requirements. So on their own, without any relay system, they benchmarked these models on highly complex math datasets. The small 1.7B model scored an average accuracy of 42.5%.
Not great.
Not great. And the massive 8B model scored 54.1%.
Leaving an 11.6% capability gap between the cheap local model and the expensive server model.
But when they applied the RelayLLM framework, allowing the small model to dynamically call the large model mid-generation, the small model's accuracy shot up from 42.5% to 49.52%.
That is a huge jump.
Huge. It recovered roughly 60% of the performance gap between itself and the massive teacher model.
It dramatically elevated its own reasoning capabilities just by asking a few questions.
But here is the statistic that changes the math on everything we just talked about. To get that massive jump in accuracy, the RelayLLM system only invoked the large model for 1.07% of the total generated tokens.
Let that sink in. For roughly 99% of the words and numbers generated during those complex logic tests, The small, cheap model was doing the work entirely on its own.
It only needed the massive server model for basically 1% of the heavy lifting.
Exactly.
If you're an app developer listening to this, that 1.07% statistic is the difference between going bankrupt on cloud API calls and running a highly profitable local-first application.
It's a total game changer.
Because compared to that old router method where you send the whole problem to the large model, RelayLLM offers a 98.2% cost reduction while achieving better performance.
It definitively proves that our prior architecture of offloading entire queries was profoundly wasteful.
And reading through the methodology, it looks like they wanted to test if the small model was just acting as a good manager or if it was actually learning.
Oh, yes. This is my favorite part of the paper.
Right, because did they test the small model's performance after this collaborative training, but like without giving it access to the large model at all?
They did.
Yeah.
They ran what they called a teacher-free setting. They essentially locked the door to the server. They strictly forbade the small model from outputting the call tag during the test, forcing it to face the benchmarks entirely alone.
No lifelines allowed. So what happened to its baseline performance? Did it drop back down to that original 42.5%?
Actually, it went up.
Wait, really?
Yes. The researchers call this the ghost teacher effect. On the easier math datasets, the small model's baseline accuracy hit 61.12% completely on its own.
Whoa.
That is significantly higher than a standard small model of the exact same size.
So it got smarter even when the big model wasn't there to help.
Exactly. By constantly collaborating with the genius model during training, by passing the baton, watching the expert solve the tricky 8-token bottleneck, and then taking the baton back to finish the problem, the small model actually internalized the reasoning patterns of the large model.
It rubbed off on it.
Yeah, it didn't just learn how to delegate, it learned by observation.
And we know it wasn't just like memorizing specific math formulas because they took this newly trained RelayLLM and threw it at completely unseen non-math domains.
Right, to test its generalizability.
Yeah, they tested it on general knowledge and trivia benchmarks like MMLU Pro, which it was never trained to collaborate on.
And it consistently outperformed the baseline methods there too. It's successfully generalized this help-seeking, highly logical behavior to completely unfamiliar inputs.
It was able to recognize its knowledge gaps in general trivia just as effectively as it did in algebra.
If we connect this to the bigger picture, it's just incredible what this means for model training.
Well, for you listening, this deep dive points to a massive paradigm shift. We started by talking about the brains versus budget dilemma, right?
Yep.
But RelayLM suggests that the future of AI isn't just massive, expensive cloud servers hoarding all the capability while our local devices run basic toys.
Not anymore.
The future looks like highly capable, hyper-efficient, smaller models running locally on your laptop, your phone, or your smartwatch. They do 99% of the work locally, saving your battery and your data, and they only ping the massive cloud AI for a split second when they hit a true cognitive wall.
It democratizes access to state-of-the-art reasoning without democratizing the massive carbon footprint that usually comes with it. We are moving toward an ecosystem model.
Swarms of tiny, self-aware delegates.
Exactly. Collaboratively solving problems with larger hubs, passing the baton back and forth for literally pennies on the dollar.
So what does this all mean?
Well, it leaves us with a really fascinating implication to consider. If small models can learn to dynamically pause and force large models to generate answers in tiny 8-token increments, could this be the key to solving AI's black box problem?
Oh, wow. I hadn't thought of that.
Think about it. For years, we've struggled to audit the reasoning of massive models because they output entire complex thoughts all at once. But if a small model acts as a highly structured controller, it essentially forces the genius model to show its work, step by step, token by token.
Because it's breaking it down into tiny chunks.
Exactly. We might finally have a mechanism to actively supervise and audit the deepest logic of our most powerful systems.
That is an amazing point to end on. To everyone listening, thank you so much for joining us on this deep dive. Keep questioning the world around you, and we'll see you next time.